So in this example number 3, let's discuss about how we would do for infinite life. Let's go back to our previous example, the one for ductile materials. So we will stick with the problem with the Roth ferrous steel. We had all the information. Now, the only thing that we are doing different in this problem is we want to solve, you can pause the video if you want to take notes on this, or take a screenshot, whatever actually works. The only spin that we are doing different in this problem is we are not given the life of the structure, and we are asked to design for infinite life. For infinite life, what you should keep in mind is when we are designing, we go back to your SN diagram. Remember, your this is alternate, this is N, and you're really designing something like this. This is what your diagram looks like, where this is your endurance limit. So what the goal is to find a Goodman stress that is less or equal than the endurance limit that's somewhere over here. Okay, so what we will do is we will iterate the problem many times. So just run your MATLAB code until this really happens. So let's say I'm going to start with a value of D from the previous example, so we can just build upon that and work as a review. So what we know the fact that I need to solve this problem every single time I start, and this is a done deal. Okay, your problem, we only did this for all 3 problems, and the load hasn't changed, the uh, design factor hasn't changed, so these values will be the same. And then I'm going to find the alternate and the mean for all my loads. I would come here. Now note that for every iteration that you choose, your KT will change. My suggestion is the following. Let's go ahead and optimize this is how I do the problems when I approach them. Let me optimize a D, keeping my KT constant for my first iteration. And once I get close to my D, then I will come back and I will iterate in trying to change this. Otherwise, it becomes a cumbersome exercise, and you have to keep on finding this for every iteration. It's a little more tedious. So again, I'm going to keep these values the same until I think I have reached an optimum smaller D. Remember, this is the one that you want to optimize, never the bigger D. Okay, so that's what I will do. And this is just because the ductile materials. In ductile materials, this is going to vary. Same for brittle materials. And then not to say that my notch is not going to change. So I'm going to assume my notch remains identically the same. So these values will actually be fixed and will not change in my problem. We will assume that these values then remains the same for the first couple of iterations until we get close to your diameter that you're looking for. So, and again, this problem, this is going to remain the same. And I want to just run the MATLAB code and tell you really how to go over the MATLAB code and the results one more time. It works as a review and tell you how we do the problem. So I'm going to start with my problem with a smaller d equal to 0.0. And let's see the value of my SE compared to your SE. Okay, so those are the 2 values, or we can just actually try to do a table. How about we just did a table here? Okay, a nice table, and put different values. So the first value that I'm going to do is 2.0. Okay, and let's see the values that we get. So we go back here as usual. You're going to go, you're going to find, you're going to have many cases for ductile materials. Just wanted to go over this very quick here. When you run the code runs this for many cases. If you remember from our course, the way I gave you lectures, you can solve everything for von Mises. You can also do it for principal stresses. The plasticity actually is using your assuming that k is equal to 1, and then non-conservative approach is actually finding a KFM, and then this is usually traditional for case where KFM actually equal for your mean KF for each one of the load, just take it equal to KF. That's the approach I'm going to focus on in this example, but your code gives you all 6 values. So that's why it has A, B, C, D, E, F. And when you start seeing the plots, you see a bunch of plots here, but really saying this is case 1A. This is done, and this gives you the plots in JPEG and PDF and PNG. This is for the plastic case. It's a non-conservative. This is traditional. Okay, so we're going to stick again with von Mises. That's what we're going to do. And we're going to stick with traditional. But you can go and show yourself that you will not be that off if you use S1 either. For brittle materials, that's what I like to do. So we run the code, and then this is inches, KSI. The load, design load is 1.5. This is 50,000, 0. I don't have bending moment. If I did, then I have to include that value there. 18,000, this is 0. In the case, this is the case that we are working with is torsion combined with axial. So this is case number 3. This is circular. I'm going to start with my first guess, d equal to 2. And we found this is 1.8. I really don't care for bending because we don't have bending in this problem, but for your homework you will. So you have to add that value there. I'm working with steel, so the problem calculates these values for you. And the ultimate was, I believe, 90. And the notch radius is 125. Let's assume our notch radius doesn't change throughout the problem. Okay, simplifies our analysis a little bit. Then you move on, and this is ductile material +1, and then it's asking for this again. So this was for the same value I put up here. This is 70, 70. This is 90, and these values come from the problem. Okay. Now your endurance limit, what is it? We talk about this. This is 0.5 times your ultimate for steel. So just enter the value exactly. Okay, it's 45. You cannot write 0.5 multiplied by SC. It's not going to take it. So SUT, sorry. The correction factor is 1. It was 250 degrees. You're working with hot roll, number 3. You can see that your code actually gives you all this, all the math that you actually need, how this is done. 95% reliability, no other miscellaneous factors. This is happens at 10 to the 6. Endurance limit starts there. Then you run the code, and then again, it's going to solve for many, many cases. And let me just show you the final answer that I care for. So these are your final answer. Just note that I'm using SN ductile von Mises traditional 3C. And this gives me a value of, this is 22.23. This is 43.95. So if I go here, you can see that this is actually, this is not infinite life. It is not, at least on this line. And then same thing here. You can see that I'm not here, right? This is where I would like to get. So what you do in the problem then is, then you will go here, and you will write those values that you got from running this one case study. And you find a value of, this is 43.95, and this is 22.23. So you will like this value to be less or equal than this. So this means I need to increase this value. So let me do another iteration. I'm going to do iteration, let's say I'm going to start with 3 just to see what happens. And I'm going to skip these steps and just write the final answers. I'm going to pause the video for a sec. So the value that I get is 11. 11.88, and this is 22.23. This is not supposed to change as expected. So let me write this again. 11.88. So you can see that it actually is bound with these values, and I'm going to keep iterating. So I will just write here the final answer now. And I do this running the code many times. Okay. Now know that when I did my iterations, you will find that I got very close to this value. Okay, this value is very close to this, and now this is a very good time to recalculate this, but let's find our new KTA. Okay, and KB we can take it equal to 1 just because we are not using this, and find the new KTS. To do that, we go back to our charts. Okay, go into your charts. Know that your bigger D is actually your R plus D plus your R again. So it's 2.5 plus 2 times the radius, 0.25 divided by the small d, 2.5. So this value actually comes to 1.10. So it's this value right here, and this value is approximately there. So we can this is 2.0, maybe about 1.9. So we can say my new value would be actually 1.9 now. And then for this, it's actually the same. This would be 110. This will be 0.5. And let's find this value. This is here. This is 20. So maybe the next, this is 1.09. Maybe you are between these two values. So maybe somewhere there, if you would. And again, I'm just eyeballing these answers. So maybe 1.45. So now I'm going to run this whole case again, but with KT equal to 1.45 and 1.9. I need to iterate this. I need to change this because remember, your stress concentration factors will change, and I don't need this, so that's why I'm going to use equal to 1. Now that I got very close, it's a good time to start iterating by changing this in every iteration. So I'm going to go ahead and do that. I'm going to pause the video, and then we will see the answer. So the value I get is 23.28. It's very close to 22.23, but I have gone above. So that means I need to slightly increase this diameter. Let's see what happens if I do 2.55. If I do this, I need to change this as well. I want to be as exact as possible. 55, 55, let's see what we get. So by changing this, I really don't improve this by that much. It's 0.049. So it's about basically 5. This is 1.098. It's 1.10. So this is not going to change at all. So for this iteration, we can use the same numbers. So we run this and we find this is equal to. So when I solve this, I find this gives me 22.10. This is actually pretty close to your endurance limit, and you can see that this number is still less than this, so this is actually going to be infinite life. So this is the number, this is the recommended diameter. So for infinite life, your recommended D will be 2.55 inches. Um, that is a design diameter. And for this is infinite life because your S equivalent from Goodman stress actually equal to less or equal than sigma is equal to your endurance limit. So this is how we actually design for infinite life. Um, so this concludes this example.